Welcome to MCH 2022, Day 4 Intent Battery. You probably know that battery, no, we are not talking about batteries, but battery-powered cars. So here with me on stage is Martin Herfurth to talk to you about demystifying Tesla's Bluetooth passive entry system. Please give him a very warm round of applause.
Thank you very much for the introduction, and thanks you for being here. I'm talking about Project TEMPA today, and this is, as you can see here, about Tesla cars. It's the 4th time that I'm giving this talk, but actually I was adding quite some new stuff as well. Every time I did it, I tried to make an effort and add some new things. Right. So about Trifinite.org, you might have seen the logo in the lower right. It's a group logo that is almost pretty retro already, because that was 18 years ago when we started, together with, or more than that, together with Colin Mulliner and me, and we did a lot of Bluetooth-related research. Back then, of course, mainly Bluetooth Classic, and we were participating in some test events with the Bluetooth SIG, which is the standardization body for the Bluetooth protocol. And we were helping vendors back then with their not smartphones, with their feature phones and Symbian phones, stuff like that, in order to have like not the easy low-hanging Bluetooth vulnerabilities. So, and about me, I'm from Salzburg, Austria, pretty much like the Herald. He's not from Salzburg though, he's from Vienna. And I'm a regular participant and also speaker at some instances at C3 in Germany, which is the yearly CCC Congress since '98 without missing even one. And I also am the author of the Tesla Radar app, which I will talk a little bit about later. And of course, I own a Tesla myself, because always renting or having to rent one in order to do tests just didn't work out for me. And a little bit of memory lane. My first camp that I participated was actually in 2005. It was What the Heck. It was in Liende, also in the Netherlands. And I found a picture of me talking like in one of the old Flickr accounts that is still linked up in the page. And as you can tell, no difference, right? And back then I was talking not only about Bluetooth security and stuff we found. One of the projects I was talking about back then was also Car Whisperer, my first project that went into the automotive direction. And what I did there, we were injecting audio messages into cars with hand-free sets, and that was a lot of fun. That was possible back then because of the standard PIN everybody used. So it got a little more complicated with Teslas. They use, obviously, not a standard 4-digit passkey in order to unlock the car. They do it for driving, though, as you might know. Maybe as a show of hands, how many of you do have a Tesla or drive a Tesla? All right, so that's like 500% more than usual, because usual is just one guy, me. All right, but that's at least some more. That's cool. And this talk is about telling you why you should be really careful using the Tesla phone as a key, and also like the NFC. Some of the things have been mitigated, but Project TEMPA was investigating the Bluetooth low energy interface that Tesla has in their cars. And this interface that I'm talking about is primarily found in all Tesla Model 3 and Y, but also on the new facelift variants of Model S and X. So it turned out that this phone key feature, which got introduced with Tesla Model 3, turned out to be a quite popular thing, and I believe it's also going to be in the Roadster whenever this appears. And it's like the thing that Tesla puts all their effort on. And it's just an estimation that about 2 million cars to date do have that feature. And what it also allows is not unlocking the car or like driving it. It's also like having a continuous ID, so tracking and identifying vehicles on the radio level is pretty easy. And also you can like send messages there. And how you do that, I'm going to show you. So most, or not most, some of the things have been fixed by Tesla over the time, some of them partially. So I talk about one thing that got mitigated, but kind of reopened by one of the attacks I'm going to show today. And all the, or most of the things are findings that came from reverse engineering the official Tesla app, which is an easy process, as you might know. The only thing is, of course, they use obfuscation, so you have a lot of guesswork as well. So the original research started with Tesla radar in 19, but it intensified in 2021 when playing a little more with the app and looking into that communication. All right, phone key. What is it? It's like the big innovation that they had. You use your phone as your car key. And that's a pretty good idea. And as said, it's going to be part of future models. So what's like the ways to unlock a Tesla? Of course, you guys that own a Tesla already know that, but for the ones that don't, I explained that in a short slide here. So you have like your phone, which is pretty capable of using like the network-based API, which you require to have internet for. Then it's the NFC protocol, which is in purple here, which is used for directly interacting with the car. And then you have Bluetooth, with kind of in the middle. And as said here, VCSEC is the protocol which is spoken from the phone and also from the key fob via Bluetooth Low Energy to your car. All right, NFC card. These are the ways, you can read that later on, to unlock. I just summarized that here a little bit. And due to timely constraints, I'm also not going to show the videos, which I have like linked in the presentation, and that's going to be your homework to show afterwards, or to watch afterwards. So a little poll for the 5 people with Teslas. So how would you unlock your Tesla usually? Like with the key fob, with the phone key, or with the NFC card? Show of hands, like key fob. 1, 2, 3. And with the phone key, 1, 2, 3, 4. Is that right? All right, and with the NFC card, still 1. All right, good. So that was the official result from the Tesla, from the Twitter poll I did. So like 83% back then are using phone key, including myself. I do own a key fob though, which costs a fortune for, I think, what it is. And right, phone key is the thing the most people use. Usually, how does that work? The smartphone finds the vehicle. It has some indicators that show that this is the right vehicle to talk to, and it connects. Because the car would act as a BLE peripheral, implementing a generic attributes service that you can interact with. And there's no pairing required, and this has also some background, maybe why this is not required. And of course, you can unlock your car, you can start, you can open the frunk, do stuff like that. So whenever this car advertises a GUT service, there will be a name, like a standard attribute or a service, and also a to-vehicle characteristic and a from-vehicle characteristic, and it pretty much also is very intuitive what's going to be done with these characteristics, I guess. As well, it's exposing an iBeacon structure, and I think that's mainly done in order to have iPhones natively detect the car with all that background process optimization. I think they built that in because Apple makes it really hard to have a background process that does not rely on Apple technology. Yeah, and the advertisement is like pretty easy to find out. So there's this UUID, and then they have a major and minor ID, which is part of the iBeacon specification. And these are like the attributes that an iPhone, along with the device address of the car, would recognize the car for it to be connected. And as well, the name of the vehicle has some cryptic input cryptic stuff, right? So whoever scans for BLE devices next to a Tesla will find a few of like these names starting with an S, and then there's an 8 bytes hex sequence, hex encoded sequence, ending with a C in the most case. I guess most of you found that already. So C, I believe, stands for the center interface. Then we have a driver side, passenger side, and a rear side. But these names are guessed because like passenger side on the right-hand drive would be the driver side. So I think they kind of messed up there already. So, but the 8 bytes in the hex seemed random to me at first. And they seem to be unique to a vehicle. And they are always turned on and unique to the vehicle, and that kind of led to the thing with the permanent ID. So anybody with a phone could tell whether my car is in the proximity of Bluetooth or not, which is a privacy issue, which I pointed out in 2019 to Tesla. And that's also when I published the Tesla Radar app, which is a showcase for how easy it would be to spot a Tesla over a larger area, given that there's enough people with a Bluetooth phone participating in the Tesla Radar ecosystem. And in a way, it is allowing to stalk people, right? And even though the Apple AirTag implements way more security and privacy features in their AirTag technology, so they randomize their IDs, they are really hard to really track and reliably track. But even this caused a massive outcry in the privacy community that this is not a thing that they should do. Of course, slipping a Tesla into somebody's purse is hard, but that would be maybe the reason that Tesla permanent ID never got that of an issue. So I had a correspondence with Tesla, and they said, well, we know that is the case, but we don't change it, because as long as there's cameras everywhere that also film your number plate, we don't see a reason of changing anything there. So I think that was the reason when I made that app public and kind of show how big of a thing that could be. And first it was for showcasing privacy issues, then it was a game for Tesla fans, so there's some gamification in there, there's a ranking. Actually, Thomas right here in the second row is like the #1 Tesla spotter for a long time. And yeah, give him a... And I don't know how many 10,000s of Teslas you spotted, but you're like the #1 spotter, even though you're not on that ranking list anymore because your super observer is currently under maintenance, right? Right, but very good work. And of course, it's a big data collection for work. I think there's a statistic from May, and there was about 154 unique cars in the network from about 50, in the meantime, 50 different countries. So there's a lot of players, and if you found this interesting, I have to say at the moment I'm having technical issues with the app, so just allow it communicating on Wi-Fi, please, if you want to use it. Because it kind of retransmits a lot and causes a lot of, and I have to find out about that. So, but back to the thing with the eight characters that are hex encoded, or 8 bytes that are hex encoded. And of course, it's unique to the vehicle, and the VIN would also be, like the vehicle identification number is also a thing that is unique to vehicle. So it encodes a manufacturer ID, a model type, and so on. And that is hashed, I found out. Hashed with a SHA-1, and then they cut out, like they butcher it up and say only the 8 bytes are taken for the vehicle identification. So it's really hard to reverse that process since it's a cryptographic hash, right? So what I did is creating a rather small rainbow table of about 20 gigabytes, and it has a pretty high hit rate. So I can track back from that 8 bytes hexen code, I can see what the VIN is and can also see what the model would be of that kind of identifier. I also could find out like if it's a performance model or worth stealing if I'm behind a locked garage door. So it's a pretty high hit rate at the moment. I will have to add new VINs to the index. So the Austin Gigafactory has a different signature. I would have to add that. I didn't even do that now. But there's a little room for improvement, but it works rather well. And also what I did at Christmas when I found out about that key VIN or like this VIN reversing thing, I thought it would be interesting to take my new tripod and mount an antenna on top and put it in my car. So the side pocket of the Model 3 is ideal for doing that. So I put that with the antenna and went through whole Germany to the Gigafactory 4. And because I'm in Salzburg, which is way down there. And I drove along where the new battery factory is going to be, and also Giga 4, and there's the highway, and always aiming my antenna inwards, right, to the premises. And what I found there was a lot of research prototypes, and you would know from the VIN they do have an R, which is interesting, but was interesting, there was a lot of BLE, like carjacking devices, things that could be, when you tamper with them, pretty dangerous for the people working there. But as everybody knows, Tesla doesn't care a lot of people working there, right? So, and actually, this is a video that got presented in May, and it's been a similar video 2 days earlier. So that's part of your homework. You have to watch that several times for the YouTube algorithm, please. And it's about how you would pull off the relay attack. I will talk about that a little later. And also there, being able to do a relay kind of triggered me and said, that's too easy, right? I contacted the bug bounty team at Tesla again and told them that I believe this is an issue because what really happened, I tried that the first day and I had like this 2 Raspberry Pis connected and I had one in the car trunk and one in my office and I was able to just drive around as long as in the office my phone was close to that relay, right? I was able to drive to Salzburg, like 20 kilometers away. I always had my key card with me because just as a fallback solution, just to be able to drive it without the phone. But the thing was, that was too easy because it was a Gattaca setup with 2 Raspberry Pis, like really, really cheap. And Tesla says, yeah, it's a known limitation of the protocol, but in order to be safe, please use PIN to drive, which is a 4-digit numerical PIN that you would have to enter before you are able to drive the car, which does not really mitigate the risk of being robbed, right? There's also a lot of stuff in the car, which is unsafe in the end, right? But also, I had a similar attack, and also I tried to present that at Pound to Own, and they said, no, it's out of scope because it's not too binary, or it's like you have to have a key for that, and we don't even have that. Right. So, and I was interested then, so what are the security features that you have enabled in your car? Is it 1, none? Is it 2, Sentry mode? Is it 3, PIN to drive? Or is it 4, both? So 1, none. Who has none? You have none of these features? All right, 2. Sentry mode, who's using that? All right, 1. And who's using PIN to drive? 1, 2, yeah, quite some. And both, Sentry mode and PIN to drive? All right, so that's a little bit of a trick question because Twitter only allows one answer. So combined, the lower 2 showed that only 1/3 is protecting the car with PIN to drive. That means, like in many cases, attackers would be able to drive your car away just by doing a relay. And for some reason, sometimes this other Raspberry Pi on the picture disappears. It's LibreOffice, I don't know why that is. But that was the setup for the thing. So to the left side, you see the phone. Then you see the Raspberry Pi number 1, which is running Gattaca. On the right-hand side, there would have been the other Raspberry Pi, also with a Bluetooth dongle, and talking to the car, right? Gattaca allows you to see all the messages flying by there, like hex-encoded bytes stuff, right, which didn't make a lot of sense, but you could intercept that, and you could also inspect that and inject that, and you could do some on real-time modification of the stuff you see. But it started making sense when I was digging a little into that, and I said there's these characteristics, and you can pretty much tell that this one is like in direction of the car, and the other one comes from the car. But what really turned out to be happening there was a protocol, and that's the VCSEC protocol. And that's a protobuf-based protocol, and you found, it's easy to have found like indications that this is used for that. And it's used for phone key fob, for the tire pressure subsystem, maybe for backend communication, because there's some messages in there that would imply that, and also maybe for other use cases. So it started in app version 3.3.5, and you have to see that the Tesla app, the official Tesla app, is for a lot of more products than just for the Model 3. So that's why it's not version 1. So they use it for the Powerwall, they use it for S and X and older models of the car, and also now for the Model 3 and Y that have that phone key feature. And that's why this has just been introduced in April 2018. And as said, this protobuf file, which is like a description of the protocol, was really easy to extract with the PBTK tool in the beginning. But they made that a little bit harder with version 4 when they switched library to Wire, which is also the same kind of protobuf implementation, but just by another vendor and different regime, because protobuf is Google, right? And it has a very similar output, and I'm going to show you a little more of these messages soon. So as said, this is the history, so I just took like one protocol file of each version, and you see there's quite some growth over time. At the moment, I think this is not even up to date anymore, so it's been 2 months or 2.5 months since there. 77 messages, 45 enums, which I graphed out on this really small image. The blue things are the things that are referenced in the code on the Android app, because that was easy to find out. So what's actually active code use? And these, of course, were the interesting bits to look at. And also, like if you see, and that's like the first example here, you see like with the green prefix, this is the length of the thing coming, and it's not easy just to modify the length and do some buffer overflow, so this is optional, right? But from there on, the message is encoded, and having that proto file that you were able to extract, and now is also like available in the VCSEC archive on GitHub, you can decode that message with the Prodoc tool. And what's happening is like one of the easiest requests is to see what are the whitelisted keys in that vehicle, and that's an information request, and you do not have to be authenticated for that. It tells you all the key IDs, and you could also get the public keys of the enrolled keys, which is not a big deal because it's a public key half. But what's interesting to have seen is that there is a service key in every vehicle. You can like use it, and it looks like from the signature as if it was an NFC key. And this NFC key has a public key that did not change a lot. So I think for years and years, they're using the same service key, which makes it a little bit of a risk that once one of these service keys surfaces on eBay, this is going to be a problem. But this is not what we are talking about. So we have like also NFC keys, the ones that you get as an owner. These are looking like that. They do not have a crypto counter. The phone key does have a crypto counter. It's a rolling key thing, and that has to do with being able to have the passive unlock functions enabled. So like without touching your phone, you would be able to enter the car like in any other keyless systems. And that's what a key fob would look like on that level. Of course, these whitelist entries are connected with roles that imply permissions, and the service key would have all of the permissions, all the 9 permissions that are defined in the protocol are given to the service key. Makes a lot of sense. And usually as a phone, you just have 4 of those. It would be the local drive, local unlock, and the remote unlock and remote drive. The NFC cards also have the permissions of adding stuff to the whitelist, because it's necessary once you have that NFC card, you use it in order to whitelist your key. And there's a message type from VCSEC, which is pretty comprehensive because it contains all the kind of sub-message types that are possible to be sent from the card to your phone. And of course, there's also like one of the most common examples. You see an authentication request here. That's whenever you pull the handle, it's from VCSEC and you message to your phone, and you would have to answer it correctly for the card to unlock. And also, there's like a command status, a vehicle status, where it tells you whether it's locked or unlocked, stuff like that. And then the other side of the spectrum, you have the to VCSEC message, which embeds all kind of stuff. So unsigned messages come also in a few different things. And these are used for messages without a direct security context, but are also used in order to encapsulate messages in a signed message that do have a security context. And that's a signed message there. And as the name implies, you've got to have cryptographic keys in order to do that. And VCSEC uses asymmetric keys based on the elliptic curve cryptography key pairs, and that's like the OpenSSL command in order to generate a key for that yourself. And what then happens once you whitelist that key and you know the protocol, you would have to tap your NFC card, but then shared secret is derived via the Diffie-Hellman key protocol, and then you can use your key with the car once it's whitelisted and send signed messages to it. So that was a lot of guesswork, but I finally got that working. And the crypto algorithm used for the whole process is the Galois counter mode with associated data. It's best known from SSH because it's a really stable implementation, it's really secure, and it's a very good match for the use case. It implements a rolling code, so you have the crypto counter that always has to increase, and then you have additional data, which is used as a challenge response for the passive entry functions. And it's intending to prevent replay attacks, of course. Also the rolling code. There's some differences though. The shared secret is 16 octets, but the invocation counter or the crypto counter for the GCM usually is 8 bytes. Tesla is using 4 bytes for that, and that's also making sense because 8 bytes, if you see like every keystroke with SSH needs a next value, and here like every signed message that you send to the car is like 1 counter up. So it's like 4 bytes is already a lot for that. Right, and there's different signature types that also become important later on. So you have like ones of the GCM with and without a token, or like the present key also as a signing method. There's like different actions. I don't go too much into detail here. You can read that on the slides, which are online already, and also like in the VCSEC protocol archive. It's different things. Signed message example, you see there's a protobuf message as bytes encoded in here. Then you see the signature type it has. There's the signature, key ID, things for the card to verify the phone I'm talking to possesses the secret key that I do know the public key of. What can you do with that? Since unrestricted requests include that you can enumerate the keys, you can see how many keys are enrolled for this device, for this vehicle, how many Apple, how many Android devices are there, how many NFCs. You can find out about that. And the process of whitelisting a key just requires you to have like that NFC card. And usually you log into your Tesla account, so that's what the official app is doing. And since you have like access to the owner API with your login, you get a token, you get the VIN identifiers for all the cars that you are permitted to lock and unlock. And finally, your app goes ahead and finds the vehicle and begins the whitelisting process. It would send an information request and get like the public key of the car, receives that, and also then sends information requests to get the list of whitelisted keys. Then it tries, or it asks the owner to tap the key card, and then with that authorization on the B pillar or Fascia blade in the middle, this car is getting in the car. Finally, the phone asks again, show me again the whitelist of keys, and once this key is on there, the process is done. And there you go with the authorization timer attack. So out of convenience, Tesla decided in August last year that it would be really great if I was like, as a car owner, tapping the NFC card, would get in the car. It would be so great for the owners using the NFC card just to be able to drive without any further action, without any further keycard action, right? So what they introduced was the authorization timer. 130 seconds that do not require an extra tap for that. Bad news, because during this time frame, attackers were able to also enroll their own key in your vehicle without you really noticing it, right? There was no indication on the screen, and actually there's also a presentation in that video. It's also linked on the Trifonite page. Also homework, please watch it several times and give it a thumb. And this is about the staged thing where you can also force a user to use the NFC card, because usually if you do have a phone, you won't bother using your NFC card. But there's some situations where you, in the easiest case, just use a 2.4 gigahertz jamming device and would just jam the frequency and the phone would disconnect. And in order to get into the car, you would have to use your NFC card for tapping it. And there you go, the authorization timer attack would have become possible. And owning a key on the device does allow you to lock and unlock the vehicle and to drive the vehicle. But that's also when Tesla said, yeah, use PIN to drive, so people with the key cannot drive your car. They can rob everything from the interior, but not driving, because you have to enter that 4-digit key. And that's when I did another video that shows how easy it is to bypass this PIN entry just by sending that remote drive command to the car, which was intended to be used in the summon feature, where you can say, like in the parking lot, please car, back out of that really narrow space because I want to get into that. And this PIN to drive dialog just disappears when you send that command. So Tesla was not really happy about that information getting into public, but right. And then there's something else which is fun to play with. Tesla has a really broken trust model. So I put in here Cartman there, you know that, and it's like that. The Tesla car always would say, respect my authority, and would not even ask that. So every message that is sent from the car to the phone is trusted by default. So the car never has to prove to the phone that it's really the car, right? So this is an issue. The other way around, of course, the phone would always have to prove by signing a message, it would have to prove I'm the real device, right? But not vice versa. And of course, that's like the next step was how to emulate a car. So the phones will talk to me instead of the car. And of course, you would have to expose an iBeacon structure like the car also would do. And then it was a little bit tricky because you would use the extended inquiry format in order to the extended inquiry response, which is not easy to do with the BlueZ dbus API, which I was first trying to use there. I ended up using a Python library, which is able to do that. And there you go, and you can look like that Tesla car, and you also would have to use a BD address and set your Bluetooth address accordingly. But once you did that, any phone would talk to you thinking you're the car. And since you never have to prove you are the car, you can tell it bullshit. Like, hey, your key is not valid anymore. So once the phone would connect, I would say, please send me an authorization. And the phone would go ahead, send that authorization. Next thing happening, the car says, sorry, you're not on the list. It's like a bouncer at the disco, right? And the phone would go ahead and say, show me the guest list. I'm sure I'm on there. And the bouncer would go, see, it's an almost empty guest list. You're not there. And then the phone is convinced and says, right, I drop the key and I say goodbye. I don't bother you anymore. And that's how the key drop attack works. Users locked out would have to use the NFC card in order to get back into the car, which opens that window of that authorization attack where attackers could put their key in the car, right? Again, it's like a little tricky, so be careful when having like issues like that. But it turned out that the key that was stored in the device, in your phone, was not really deleted. So it was dropped, but it was not really deleted. That means next time you talk to the car, it would be clear in a short time that the car knows the key and your phone still knows the key. So it's kind of a soft restoration and not a full key enrollment. So again, this could be attacked by, there's a small demo. I will skip that. This just shows how the tool works in order to drop the key of a car. Pretty easy here with the evil bit. This is not anymore in the current version. So it's like a little different naming there. But you see how you present that car with that almost empty guest list in a way, and the phone just disconnects. So, but there's a new attack as well, and that's new for this conference here. It's the crypto counter confusion attack. And the thing is that you cannot only tell the phone that you're not on the guest list, sorry. You could also say, well, that crypto counter you used is a little bit smaller than expected. I could make up an analogy story for that, smaller than expected. I don't do that. So the phone key will ask, and when you tell it, right, so this crypto value is too little, too small, because it's not allowed to roll back that counter for a reason. And Tesla is really strict with that and does not allow the crypto counter to be lower than last time because of replay attacks. And of course, there's also confusion going on. So the phone app will ask the car, so, all right, it's smaller value as you expected, so what is the value that I should use in order to send you signed messages? And the phone, the vehicle or the fake vehicle would say, well, how about 4.2 billion? And that works, right? You can set all the 32-bit value to the maximum, and that is putting also some trouble onto the owners, because as you know, the key is not deleted. Even when you say in the app, all right, I delete the key, re-enroll it, it's still in there and the counter is still that high. So usually the owner would have to reinstall the app in order to get rid of that old key and being able to enroll a new key for the same car. And if you combine that with the key drop attack, this is even faster. So it really is a mess at the moment, so the state model of the car just do not play very well with that. And it's funny to have seen that the iOS app allows a maximum value of 4.29, an unsigned in 32, but the Android app is using a signed in for that verification, so just half of the value is allowed as a maximum value to tell the phone to be using the next time. And what's happening if it's at the highest value, so the counter cannot be increased anymore, so the phone is no longer able to send signed messages. It's pretty much useless for that purpose. But if you really deinstall the app, reinstall that, have a new key enrolled with the whitelisting process, of course you expose yourself there again. But also, if there's two devices with the exact same name, which usually doesn't happen in Teslas when you enroll keys, I observed that every time I unlock the car with my new key, which has the same name, there seems to be some security mechanism to be kicking in, because what the car then does is, for some reason, it asks me to tap my NFC card on the B pillar in order to drive. There you go, key injection again. So this is opening up again that vector that every time the owner gets in the car and wants to drive, has to tap the NFC card, the attacker could enroll a new key again. So this is not good in a way. And this is another example for a message here. It's when the car wants to know like about the current counter value, so where the temporary tool would say it's like 4.2 billion. What else does it tell you? It tells you about the token which is used for that passive entry, a passive entry thing, right? So as said earlier, Passive entry is relying on a challenge response scheme. So it would ask for authorization at the car. The car would then reply back with the correct counter number, and also with the challenge, which is in the token here, built into the answer. So that means whenever the car asks me to do the passive entry, the phone would use that, encrypt the answer, so there you go, challenge response. And of course, this relies, or this process relies, not only on the counter being increasing, but also about the token being changed very often. Because once this token is not changing, you can just take that and be offline and ask, be the evil car again, and ask the car for authorization responses. And that's what the authorization replay attack or or authorization response extraction attack does. It's just that. So you get that token from the vehicle, and then you go to a restaurant wherever this owner sits, or in the airport, and you ask, and you just pretend to be the car again, and you keep asking the phone for authorization responses with that token that you have in the car, because it turned out it doesn't change over days. So it's really a long time same token, pretty bad, right? And then what you do, you collect these authorization responses via the temporary tool, a temporary tool, and then you dispense it with a temporary tool. Both these tools are on GitHub, by the way. So that's how easy that would work. And that's been it for the new attacks. And of course, there's some tools and resources on GitHub. During the talk, I was mentioning the VCSec archive, a collection of all the proto files extracted so far. There's like the temporary tool, where you temporarily impersonate a tester and do like stuff like the key drop attack and the crypto counter attack. And you can also see like the message you receive encoded like to human readable form. So it's pretty neat. Maybe if you need help, just contact me. And of course, the other side, the VCSec client would be the TEMPA tool. And you use that in order to send messages to the car that you craft yourself. There's also some authorization collection mode implemented in the newest version, where you just dump the authorization responses to a file that you read from a file and just dispense them from there. And there's this VCSec archive, which also comes with a decode script that help you read the messages that you receive. And there's also that tool, which is basically a wrapper for the API that I made public on Rapid API, where you can put these 8 hex-encoded bytes to, and it would spit out a VIN, maybe, or also the model for sure, but the VIN is a premium feature. And last but not least, there is an app which is planned. I plan to program that. It's like 80% ready. It's called Tesla Key. And it doesn't talk to strangers. Because root of all evil, if you may agree or not, is that the official app talks to anybody. Also at moments when this is not even plausible. So like, why should my phone open the car when I'm not even close to it? Question number 1. Question number 2, why should that be at 3 o'clock in the morning when my phone is on the charger and in the home network? Or why should it talk back to a alleged car when it's booked into the office network? So like a lot of plausibility checks, which are pretty easy to implement actually. And these will be part of the Tesla Key app, which you can follow on Twitter in order to get informed. So it's still, I think I put much pressure on me saying that this is released in Q3 of 2022, but I'm not losing the hope, right? So conclusions, relay attacks are possible, NFC keycards are dangerous, and the app should be improved in many parts, right? And also, the VCSec does not stand for Vehicle Control Security, as many and I did assume. I was hoping it stands for security. It stands for Vehicle Control Secondary, which explains a lot, by the way. And again, we see that here in that use case, also convenience, like the 130-second counter, the inability to switch off the permanent ID, things like that are like really bad for security, again. So You might ask yourself, so we were talking about the NFC card and also the phone as a key. What about the key fob? So the key fob is a little bit special, I found out. I got one, as said, but it's not talking to me. So I don't know what I'm doing wrong. I'm always nice. I got it a new battery even, and it doesn't really want to talk to me. But I'm on that and working on that. Also some credits. There is very similar work by a guy called Dax in Ireland. Big credit to him because we got in touch and turns out he's an amazing guy. Also to the maker of Getacker, Sandeep, who did the Noble Blino framework, which Getacker is using. And also to Josh Belder, who helped me with knowing about that remote drive command that makes the pin to drive dialog disappear. So you might think, well, I got that implant in my hand for starting my car. Is it too late? And the answer is, no, it's not too late. You can chop off your hand anytime. Or you just know the protocol and delete it from the whitelist, right? Also possible, whatever convenes. So thanks for your attention. I think we have like 3 minutes left for Q&A. And also here, there's a lot of links that you can follow in order to see the slides, to get in touch with me, to fund my research on Patreon, all there. Thanks very much for your attention.
We actually got 4 minutes for Q&A, so please queue up at the microphones in the middle. If you keep your questions short and the answers as well, we can fit everybody in. And I think there's also a little surprise maybe for quick and short questions. There's might be a surprise in it for you. So please.
Usually I have Mozart balls with me, but it's too hot for that now. There's stickers, Tesla radar stickers, and every questioner gets one. And you also find them on the sticker tables if you don't want to ask a question. All right.
Questions, please. Don't be afraid. Well,
all right, so maybe we have some time for demo. No, I'm just kidding.
Thanks for the talk. A short question. Can you make a very easy automation that just turns off your Bluetooth when it's on the charger and it's after a certain time and turns it on again automatically in the morning? That would mitigate a whole lot with a whole lot of effort.
It would be possible to mitigate a lot, but usually people are really used to using Bluetooth because of the smartwatch they have, things like that. It would be inconvenient to disable Bluetooth for everything. What I would like to see is a little switch in the app, right? Temporarily disable. That would help a lot as well.
It is what I do. My Bluetooth turns off at 10 o'clock at night and on again at 7 in the morning.
Makes a lot of sense.
Yeah.
Have your sticker. It's a special one. I sign it for you later. All right, any more questions?
Yeah, well, there's one more. Please, close to the microphone.
Okay, thanks. First of all, great talk.
Thank you.
Did you take a look at the implementation of BLE and especially the proximity implementation of the protocol itself?
Yes, actually, it's still on there. This is an interesting message because there was too many messages in the presentation already. So this is about an alert that you get or that I got when the signal strength or the proximity was wrong. The readout for all the sensors was too high. Actually, this is not the, there you go. So we have an alert there, and it shows that the readout of all the RSSIs was too high for this to be a real unlock event. So there's something to it, but I think it's not security related. It's just for the upcoming Roadster that does not have door handles anymore. So you get there with your key, and the right door opens. I think that's what this is for. And this was just a confusion that turned out to be generating that alert. So there is something about proximity. Maybe we talk about later a little bit more if you like. I will be around.
Yeah, sure. Yeah, I read somewhere online that the BLE implementation was...
It would also be a good mitigation.
Yeah.
I'm able to fit the last one in if it's a short question and a short answer.
I will try my best.
I have two short questions.
Oh,
Don't they use measurements of time to reply to mitigate replay attack? The modern car keys use an accelerometer, so if you don't have your car moving, your key moving, it doesn't work. Can they
two very good
implement the
questions. I do my best to be really short in the answer. The first question is like time of flight, how long is the delay? Tesla and the protocol is very generous with that. So it's like about more than 100 milliseconds, maybe 200, in order to also have like old phones being able to play the game, right? They have to be really generous there. And that also played out very well with using a VPN, which also introduces delay. Second question was, what was that?
Can't the app disable the unlocking if they don't detect
the
accelerometer movement?
So it's in the protocol already. So the phone may tell the car, "Whoa, I've been moving, so I have movement." Good. The car would then decide whether it would allow unlock. But the thing is, this message from the phone, "I'm moving," is an unsigned message. So you can inject that, and the overall decision is taken by the car, right? So it's like a stupid approach again.
And on that bombshell, I will end this talk. Please give a very warm applause to Martin Herfurth.